Today, we are unraveling a genuinely fascinating scientific mystery. I like to call it the case of the electrified water. So we all know exactly what happens when you put a pot of water on a hot stove, right? It heats up and eventually it boils. But what happens to that exact same water if you add electricity instead of heat? Just imagine, for a second, swapping out your kitchen stove for a battery. Are we just going to get really hot water, or is something entirely different going to happen?
Well, let's dive right in and look at our setup for this explainer. It's actually pretty simple. We've got a couple of standard 9-volt batteries hooked up with alligator clips, and those wires lead right down into a beaker filled with completely plain, room temperature water.
Almost immediately, an incredible macroscopic observation happens. The very second that electricity starts flowing through the water, bubbles rapidly start forming directly on the submerged wires. But if you were to actually touch the side of that beaker, you'd notice something completely counterintuitive. The water isn't getting hot. The temperature hasn't changed a single bit. Okay, so we have these mystery bubbles, but to figure out what they actually are, we need to capture them. To do that, we adjust our setup just a little bit. We take 2 test tubes, fill them with water, and invert them directly over our electrodes. Now, as the batteries run, those bubbles travel up and get neatly trapped inside the glass tubes. But as we watch these tubes fill up, another really curious thing happens. They aren't filling equally. One tube is actually filling up with gas way faster than the other one. For the sake of keeping things straight, let's logically label the fast-filling one gas A and the slow-filling one gas B. Which brings us to a massive question. What exactly are we even looking at here? Are these just water vapor particles? Like, is this the exact same clear gas we'd get if we just boiled that beaker of water on a stove?
Let's think back to what boiling actually is. When we heat water, we just cause the water particles to speed up and spread apart. They become a gas, sure, but they remain water particles. They just have a lot more space between them. And we know from everyday experience that water vapor, steam, is absolutely great at putting out fires. Keep that specific property in mind.
Because it's time for the trial by fire, literally. If the electricity just essentially boiled the water without heat, then the gases trapped in our test tube should behave exactly like water vapor. To find out for sure, we're going to use flammability as our primary clue-gathering method. All right, we take test tube A, that's the one that filled up much faster, and mount it safely to a stand. We carefully uncork the tube and immediately bring a lit match right near the opening, and we wait for the reaction. Bark! That is exactly the sound it makes. A loud bark and a literal small explosion occur the second the flame hits that gas. Now, I don't know about you, but I have never seen steam from a boiling pot of pasta explode like that. This proves, without a doubt, that gas A is definitely not flame-extinguishing water vapor. So what about gas B? If gas A exploded, what in the world will the slower-filling gas B do? Let's test it using the exact same procedure. We uncork test tube B, bring a lit match right up to the opening, and carefully observe the flame. This time, there's no bark, no explosion at all. Instead, the flame on the match suddenly burns incredibly bright. It flares up significantly when exposed to the gas. This is a totally different reaction than gas A, and again, completely different from what regular water vapor would do. When we lay these results out side by side, we have 2 completely different macroscopic reactions. Test tube A produced more bubbles and resulted in a small explosion. Test tube B produced fewer bubbles and caused the flame to burn far brighter. So, what do these visible, dramatic clues actually tell us about the invisible particles making up these gases? Remember, properties like flammability define a substance. This brings us to the absolute crucial point we figured out. Because we see entirely different flammability properties, we know that adding energy from a battery to water produces 2 different gases with completely different properties. And if the gases are different, the particles that make up these different gases must be different from each other. Furthermore, because neither behave like steam, these particles must also be completely different than the ones produced from just heating water. We literally have entirely new substances here.
But this opens up a whole new can of worms. Where did these brand new particles come from? Did we just magically create new matter out of thin air just by plugging in a battery?
Well, the answer lies in the mass. Scientists have run this exact same setup in a perfectly sealed, closed system. They weigh everything before turning on the battery, and then they weigh it all again after the new gases are produced. And guess what? The mass stays exactly the same. Not a single fraction of a gram is gained or lost.
And this brilliantly illustrates a core rule of science. The matter that makes up all of these new substances must come from matter that made up some of the original water particles. All that exploding and flare-inducing matter was already there, hiding inside the water.
So let's quickly lock in our ultimate deductions from this explainer. 1. Adding electricity breaks water apart into two completely different gases. 2. The particles of these new gases are different from each other and completely different from water vapor. And 3. All the matter for these new substances came directly from the original water particles.
Which leaves us with one incredibly provocative thought to chew on. If a single water particle can be broken down by electricity to create entirely new, different types of particles with completely new properties, what exactly are particles made of? How can one thing just become two different things? Think about that, and I will see you in the next explainer.